Welcome to our presentation. I'm Yu Han, and I'm thrilled to guide you through our project today. The project is about financial sentiment analysis and stock prediction based on pre-trained transformer models. We divide our presentation into two parts, and I will do the first part and Taiyan will do the second part. First, let's start with the background of the topic. This background consists of two key areas. The first area is the difficulty of stock trade prediction. The stock market is a typical complex, dynamic, and highly noisy system. Its price fluctuations are not only influenced by company fundamentals, such as earnings, but also influenced by a series of external factors that are difficult to quantify, such as breaking news and the collective human sentiment. These factors cause stock price to fluctuate dramatically and non-linearly. The second part is the limitation of traditional methods. Traditional methods typically use technical indicators extracted from historical price and raw data for stock price prediction, but this data focuses only on past information and market behavior, and is not sensitive to real-time information. New sentiment data can reflect the market's real-time reaction to current information, such as natural disaster and political turmoil, thus compensating for the limitation of traditional methods. Therefore, incorporating new sentiment data into stock price prediction tasks may have beneficial impact on the prediction. So this is our objective, to verify whether incorporating new sentiment data can predict stock price trend more accurately than using price data alone. Next, I will talk about the related work. For sentiment analysis tasks, we usually have two kinds of methods. The first is the lexicon-based approach. It is pre-prepared dictionaries or sentiment lexicon to determine the sentiments of text. It is widely used, but the limitation is when dealing with financial terms that have unique characteristics, such as bull or bear, the dictionary may not be able to accurately capture their contextual meaning. The more suitable method for this task is a machine learning-based approach. This one treats sentiment analysis as a classification problem and predicts test sentiment by training a machine learning model on labeled dataset. Due to its superior performance, models based on transformer are widely used, such as the BOT. Based on numerous models, our second goal is to explore whether general transformer models or domain-specific models are more effective for stock price trade prediction tasks. Next, I will talk about the stock price prediction model. It has three kinds of models, and the transformer-based model performs better than the other two kinds, and the informal model performs even better than the classic transformer. So we choose informal model for our price prediction experiments. So next, we come to the third section, method. This is our overall flowchart. First, we propose the two datasets, and this is step 1. Then step 2, we make sentiment analysis on processed news data. And step 3 is we use sentiment classification results and the processed stock price data to complete the price trend prediction. The two datasets are obtained through the Alpaca Marketing API. It covers all the data from 2024 to 2025. The news data and the price data are aligned with the timestamp. The processed news data is used as input to 5 models. The bird and distant bird model are general models, and the other 3 are financial domain-specific models. The result has 3 polarities: positive, negative, and neutral. Then we apply the resulting sentiment prediction and the processed stock price data to the input of informal model and obtain the stock price trade prediction. Next, we come to experiments. First is dataset. For news data set, we obtain the real financial news data programmatically through Alpaca News API. It covers 400,000 financial news items from 2024 to 2025. We do the data extraction to get the ticker, title, summary, source, label, sentiment, and publish timestamp of the news. For stock price dataset, it is obtained through the Alpaca Market API, specifically the Stock Bar API. It covers the same time period, and we collect daily candlestick data for all target stock during this period. We also extract timestamps, opening price, high price, low price, and other data information. After data extraction, we align these two datasets based on the timestamp. And this is the first part of the experiment. That concludes my part. Now I will hand it over to Cheyenne for the next section.
Okay, now let me show you the rest. We compared 5 transformer models, 3 domain-specific and 2 general, to capture sentiment from news. All models are implemented based on Hugging Face's Transformers library and make 3 class predictions, that is positive, neutral, and negative. We run on the financial news and summary data from 2024 to 2025, takes a probability average of multiple news for each stock in a day, and calculate People's minus PNAG as a sentiment index, and fills with historical price features to input the prediction model. Each model has the same architecture and input pipeline, differing only in its source and pre-training corpus. The BERT process is a BERT model provided by Process AI and fine-tuned on financial corpus. It is designed for sentiment analysis in the financial domain. FineBERT Tone is a variant of FinBERT, further fine-tuned on the financial phrase bank dataset, which is more suitable for recognizing financial text tone. The above two are versions of the two financial fields, which are fine-tuned based on different financial corpora and show the most stable performance. BERT Base is a general domain BERT model that is used as an out-of-domain baseline model to compare domain-specific models. DistillBERT is a lightweight distilled BERT model that significantly reduces computation while retaining 97% performance. They used a non-financial corpus as a baseline control. Financial Roberta is a model based on Roberta Large and fine-tuned on financial news to capture micro-time differences and generate more robust financial sentiment representations. And counting the results of the sentiment analysis of the 5 models, we can see that the financial domain model tends to be more polarized, showing sensitivity to financial text. FinBERT and Roberta show balanced polarities, while DistillBERT only produced binary results without a neutral class. And then we move to stock price prediction. We use 2 models, per ticker and no ticker. For per ticker, for each ticker, an informer model was trained independently. The input was past 60 trading days and the output are next 5 days. For no ticker, a single line GVM model was trained using all tickers jointly, rather than training one model per stock. And in this model, our output are next day stock price prediction. And the 2 models have the same objective: regression on next prices and classification on direction. The same model variants, price only baseline and the price and sentiment enhanced variant, and also the same evaluation metrics. RMSE for price regression, accuracy, precision, and for score for direction and classification. Let's see particular classification results first. Across all models, we can see that adding sentiment didn't really improve overall accuracy. The sentiment augmented informer performs almost the same as the price-only baseline. In fact, in most cases, the F1 score even dropped slightly after adding sentiment, but it's not all negative. The performance differences across tickers suggest that the impact of sentiment isn't uniform. It seems to help certain stocks more than others, meaning the sentiment effect is localized rather than global. So, when we look at the RMSE results, about half of the tickers actually show improvement, which means sentiment seems to help some assets, but not all. The improvement ratio stays around 48 to 49.5%, so that's roughly close to random chance. On average, the change in RMSE is slightly positive, meaning there's no overall improvement. But for a few tickers, we can see quite noticeable gains, with RMSE reductions of more than 10 to 20%. And we can make a analysis. There are some possible reasons for lack of consistent improvement. The first point is time alignment with frequency. Since it is now daily frequency aggregation, news in the after-hours press release affects the last 1 to 2 days instead of evenly affecting the next 5 days. The second is emotional dilution. Using daily averages dilutes strong events. The third point is that the sub-ticker data is insufficient. Informer doesn't easily learn the sentiment. The fourth point is that we directly predict 5 days per ticker, while the emotional impact may be mainly in 1 or 2 days. So we can make the following proposed fix. For the first point, we can do the next 1 day, next 3 days, or next 5 days split evaluation. Add a 1 day lag for emotions, or to the hour scale, if the data allows. For the second point, top case strong news. Max quantile aggregation can be used, weight by source weight, or duplication and importance. For the third point, tickers with low news coverage can be filtered. A multitask structure with shared encoding ticker head is adopted. For the fourth point, it needs to be shortened to T plus 1 main tasks, or add approximate weight to 5 days. Now let's move to no-ticker results. Let's start with the overall performance. Across the 4 mainstream models, the accuracy under the unified setup is around 0.53. That's only slightly above random chance, which is 0.5. So there's still clear room for improvement in short-term market direction prediction, no matter which financial language model we use. Precision and recall are also quite consistent, which means the model isn't biased toward predicting up or down. So overall, sentiment provides a small but steady gain, roughly about 3%. And this gain is consistent across models, showing that sentiment is indeed a systematic market factor rather than random noise. Now, let's move to the RMSE results. The Finberton and Robota models achieve the lowest RMSE, around 0.209, which is slightly better than Finbert process at 0.212. The financial domain models, like Finbert and Robota, not only deliver better direction accuracy, but also show smaller numerical errors. In other words, their predictions are more stable and precise. In contrast, the general models, such as BERT and DISTILBERT, perform less consistently, which highlights the importance of domain adaptation in financial tasks. Finally, from a market perspective, an accuracy of 0.53 might look like just a small edge, but even that slight improvement can be economically meaningful. If we use the model outputs as trading signals, for example, only entering a position when the confidence level is above a threshold, then in theory, this small predictive advantage could lead to a positive expected return over time. Also, we can make some analysis about why it works. The first point is systematic sentiment effect. By aggregating the data across all tickers, the model learns the overall market sentiment signal across industries and companies, rather than individual stock noise. The second point is time-scale matching. The unified model predicts the next day prices, while the sentiment effect has a very short half-life, and the timing matches well. The third point is large sample size. Summary training allows like GBM to get more samples and reduces the small sample bias of the sub-ticker model. And there's some future work we can make, like lagged features, top K aggregation, model fusion, calibration of emotions, and the trading simulation. So now we can make conclusions. To summarize our overall findings, in the particular informal models, where we trained one model for each stock, the results were quite mixed. Some tickers clearly benefited from the sentiment information, but on average, the improvement was quite small, and the performance varied a lot across different stocks. In contrast, the unified light JBM model, which combined all tickers together, gave much more stable results. The accuracy stayed consistently around 0.53 across different Finbert variants, showing that sentiment features capture a systematic, market-wide signal rather than just stock-specific noise. We also found that domain-specific models like Finbert and Financial Roberta outperformed general models such as BERT and DISTILBERT. Their RMSE values were lower, which really demonstrates the value of domain adaptation in financial tasks. So, in short, the sentiment effect we observe is systematic, short-lived, but also economically meaningful. Even a small 3 percentage point lift in accuracy can potentially translate into positive expected returns in real trading. As for next steps, we plan to further refine our pipeline by adding lagged sentiment features, testing top K news aggregation, trying model fusion and calibration, and finally running trading back tests. And, we can also make some improvement in model levels, like we can use LLM for fine-grained sentiment, advanced time series modeling, and multi-model fusion. So that's all for our presentation today. Thank you so much for your time and attention.